This is a flipped lecture on 4.2, which is projectile motion. Now over here, I've copied a ton of results from 4.1. So this says that the position vector is the x position times I hat plus the y position times j hat. This says that the velocity vector is the x component of the velocity times I hat plus the y component of the velocity times j hat. And this says the acceleration vector is the x component of the acceleration vector times I hat plus the y component of the acceleration vector times j hat. Now, if somebody gives you one of these, it's decently easy to get the others. If, for example, if someone gives you x of t, then you can take the slope of that, which is written dx dt, and that gives you vx of t. If someone gives you y of t, you take the slope of that, which is written dy dt, and that gives you vy of t. So if somebody graphs these things as a function of time, it's pretty easy to go get the corresponding velocities. Ditto, if somebody gives you, say, the velocities as a function of time, then the slope of the velocity graph, dvx dt, is the acceleration. And if they give you the y component of the velocity, the slope of the y component of the velocity gives you the y component of the acceleration. Pretty big mouthful. Another special case from 4.1 of all this generality was, what if ax and ay were constants? If ax is not some arbitrary function of time and ay is not some arbitrary function of time, then the total situation is that x of t is equal to x at t equals 0, which we usually write x naught, plus v naught x times t plus 1/2 ax t squared. And y of t, under these same assumptions that ay is a constant, not some arbitrary function of time, then y of t is whatever it was at t equals 0, plus v naught y times t plus 1/2 ay t squared. All of that is results from the last section, 4.1, which was basically putting together everything in the first 3 chapters. Now, 4.2 is actually just a simple special case. In the case of 4.2, there's no acceleration in the x direction. So 4.2 is what we call projectile motion. It's like I have a baseball, I may be standing out here on the street, I throw it up towards my buddy who's up here on the balcony. Okay, this is an example of projectile motion. And the thing is, gravity is creating a downward acceleration everywhere along this path. And it is creating no horizontal acceleration. So in that nice special case, which is, it is a special case, I'm going to simplify these 2 equations. There is no x component. And the y component is known to be negative g. So we put in minus g. Okay, so this is what we call, this special case is what we call the case of projectile motion. And there's 1,000,001 problems you can create out of this special case. There's one more bit of theory I want to do. You see how x is a function of time and y is a function of time? I could actually use this first equation and solve it for the time. So I'm going to do that, okay? I'm going to solve the first equation for the time, and I get t is equal to x of t minus x naught over v naught x. So now that I've used this first equation, to solve for the time, I can stick this formula for t into the second equation. I'm going to stick it in right there, and I'm going to stick it in right there. Now, that looks like a bit of a mess. But what does it tell us? We had that x of t was a linear function of time, and that we had that y of t was a parabola, or a quadratic function of time. And what we've seen here by eliminating t so that y is now a function of x, we see that y is actually a quadratic function of this. In other words, the particle follows, if this is x and this is y, the particle follows a parabolic shape. In other words, x of t was some linear function of time, and y of t was some quadratic function of time. And what we've discovered here is that if I graph the actual position of the particle, which is y of t in the up direction and x of t in the horizontal direction, so now this is not time on the horizontal axis, which is what was over here. This is now position on the horizontal axis. We see that y of t has got a linear term and a quadratic term. Okay, so y of t as a function of x of t is a downward opening parabola. And now I'm I'm summarizing the chapter. I already had these two equations up before. Some additional equations, which are pretty trivial to get from those. Vx of t was a constant, just v naught x. Vy of t is the slope of this graph, or the derivative of this graph. Vy of t is whatever it was at t equals 0 minus g times t, because if you take the time derivative of that term there, you get minus gt. You should compare that with the way Knight wrote it on page 88. He used delta t. That shouldn't trouble you. I just had t initial equals to 0, so all of my formulas here are kind of assuming that y naught refers to the position of y at t equals 0. X naught refers to the x position at t equals 0. He just called it t initial, and then all his are written, instead of having t's in the formulas, he has delta t, where delta t is equal to the current time minus the initial time. If you put initial time equals to 0 in his formulas, you'll get my formulas. Okay, that's 4.2.